Good evening, everybody. My name is Paul Servatka. I'm the president of the Chicago AMS, and this officially is the Chicago AMS chapter. It is co-sponsored tonight with the College of Dupage AMS student group. How many of our student AMS members do we have here tonight? A couple of you guys. Anybody who's interested in being the member of the COD AMS, if you're interested in this, please talk to Jacob afterward. That would be a good person to talk to. They're going to be planning some stuff for students. Specifically, we'll be doing some talks. I'm going to give you a couple of announcements here tonight before we go on. A couple things. First of all, this is what's going on right now. There's a couple of tornado warnings down in southern Illinois and into Missouri boot heel. This is the Paducah range. How many of you were here at the last meeting with Christine Wilgus? So this is her office, and so they're actually getting the tornado warnings now, and it's pretty fun to have that stuff out there. So the beginning of storm season, I wanted to give you a little understanding. I've been involved with Dr. Gensini from NIU, who is not here tonight because he's going to be on a broadcast called Weather Nerds, and he'll be doing that tonight, so he can't make this meeting. But we've started up our ERTAF, our Extended Range Tornado Activity Forecasts. We started, and we do this from March through June. And this is our 6th year of trying to do week 2 and week 3 forecasts. And you're going to be published in the Bulletin of the AMS coming this April. So take a look for that article. We did our first forecast, and we chickened out, and we're doing average forecasts for weeks 2 and 3. And there's climatology is about 12 or 15 tornado reports in that time period. But we have below average confidence. It's a pretty interesting pattern this year where there's a lot of cold air coming on the east. It's fairly active in the southwest, but it's, for those of you who in meteorology, it's a little bit barotropic, and so we don't have a lot of directional shear. We get a lot of lines, so we're not looking at a major tornado event for a while. We usually are looking for windows of opportunity when we see the pattern that will evolve in the Pacific and then eventually lead to a few outbreaks of tornadoes in the United States. So if you want to be checking this out, please feel free to do so. I also want to give you a couple of other bits of information. The DuPage County is going to be holding this is our 30th year of doing the advanced spotter training. They've extended the registration date through March 4th at noon, so you still have a couple days if you want to get involved in this. I know we have a bunch of people from my 11-15 class that are getting big extra credit. I don't know if Ron Stens is going to have extra credit for his other classes. But this is a really great seminar. How many people have had some sort of a basic training of spotters for tornadoes or do that kind of stuff? So this is the advanced one, 30 years. It's going to have a couple of good speakers. Soon to be Dr. Stens will be talking, and a couple of other people from the Weather Channel will be here, and a number of people from the National Weather Service will be speaking as well. So if you're interested, just type in Google DuPage Severe Seminar, and you'll come to this thing. Last thing is we do have a storm chasing program, and I kind of need to make a pitch. We've got 4 trips this year, and we are still looking to fill a couple of positions on trip 1, which is coming up in just about 2 months from now, a little bit less than that. So if anyone is interested in going tornado chasing with us, it is a 2-credit-hour class. As long as you don't get thrown off the trip, you can get an A pretty easily. If you die on the trip, it's an A+, as long as you've got your video camera going. But take a look at the dates. That's going to be from the end of April to beginning of May, sort of that early season, big activity, scary stuff season. And we're a little bit down this year than we've been before. So trips 2 and 3 are already full, but we do need trip 1, and then trip 4 is later into June, sort of the late season high plains, which looks to be a good year with the moisture content that's going on out there. We have a number of people who are signed up already and are talking about doing it. So if you're interested, come talk to either myself or Ron after the meeting, or just give us a call, email. That'd be great.
Where's it at?
What? If you want to just go here, if you go to weather.cod.edu/chasing, you'll find this information. These are all the dates here, April 23rd through May 3rd. We go wherever we need to go. So we take off, and day by day, we decide this is where we're going to end up. So we went to New Orleans, and that was a good time. We didn't get any tornadoes in New Orleans, but we did get a hurricane or 2, or in some people 3. So anyway, that's some things that I just wanted to take you look at. We are going to be having an April meeting. We don't have the date scheduled yet. It'll either be a Monday or a Tuesday night, and we're going to be talking about having it at Lewis University aboard their DC, no, what do you, 737?
MD-80.
MD-80.
Yeah, we just got it delivered from American Airlines. I'm Rick DeMaio, by the way. I teach aviation meteorology there. So we got the MD-80 about a month ago, and it sits 147 people, so we got plenty of room. So we'll actually hold the meeting, Paul, at least half of it, on the airplane. We'll hold half of the meeting on the airplane, and then the rest will go into the flight dispatch area, as well as the some of the areas where people can sit and pretend they're an air traffic controller or a pilot. So we have, I think, 4 simulators, and people want to take advantage of that. And then we'll sit and talk and have the rest of the meeting.
Oh, that'll be awesome.
Yeah.
So we're planning on when that's going to be, what it's going to look like. It'll be sort of a roundtable discussion. We'll have some pilots. We'll have observers at airports. We'll have forecasters for United. We're going to have a lot of people involved in the weather community with aviation. So if that interests you in any way, shape, or form, please do so.
And I'm still trying to figure out whether or not we can then walk over across the parking lot into the National Weather Service office. So it could be kind of a dual thing. If we can figure out if the group's too big in one part, we could take the group over to the National Weather Service.
So it'll be a fun night. It'll be great to do. And if we're lucky, we'll take the plane up and fly off to South Florida. And then it'll even be a way better. And if we are able to do that, I'm buying the first round of hurricanes. Okay, so keep that in mind. Chicago AMS, this is an announcement for you guys. Has everybody signed up for this year? We are still looking to make sure that we have our membership. It is $20 to be a Chicago AMS member. And we count on you guys to help build our budget so that we can bring in great speakers like we have today. And we're going to continue on this. We are also investigating the possibility of doing a May banquet like we did last year. So we'll be in touch with you sometime soon. I'll probably do it at the Maggiano's if you're interested. It was good. So we'll take up a poll online. How many of you in the Chicago AMS are getting our information through email primarily? How many of you are getting it through Facebook primarily? Okay, so we'll send it out both ways. Okay, great. Well, the next thing I want to do is introduce Skip Talbot and just tell you a little bit about what we've been talking about. Skip is one of these great visionaries of how to visualize severe weather. I got to know Skip several years ago. He's done a lot of the advanced spotter training workshops with me, and he is just amazing at putting visuals and discussing them and teaching them. And he does this with video in just ways that I've never been able to do. He has got some work with Pecos Hank, who's another colleague of his, and he's come out here. And these two are probably leading the way as far as video visualizations of severe weather. So he's got some amazing things to show you of things that has happened last year. But he's also going to be talking about storm chase safety and really safety in general in the chaser community and those who are doing spotters. As you all know, storm chasing is kind of blown up, especially after the movie Twister. And a lot of people are becoming more and more foolish. They're more and more reckless in what they're doing. And some of these situations are going to lead to certainly more deaths. We've had a couple of deaths. We've had a number of serious accidents. And these things are just going to go up unless we're really aware of facing the issues correctly head on and dealing with the safety issues. So I'm very excited to have Skip over here. So please welcome Skip Talbot.
Thanks for having me. Great turnout tonight. How many students do we have here? Lots of students, awesome. How many storm chasers? Great, awesome. Very good. So yeah, I just want to talk about kind of what I've been doing lately. I didn't prepare a big scripted presentation like I normally do for the big Dupage severe weather seminar that I usually do in March with you guys. So I just want to kind of show you what I've been working on lately and kind of talk through it. So yeah, Pecos Hank. You guys all know Pecos Hank, right? He's an awesome storm chaser. He joined our team last year. I said, Hank, do you have a shot of a tornado in a rearview mirror? Because I think it would make a great pun for my talk title. And he's like, yeah, here you go. Of course he's got one. So Thanks to Hank for the title shot. So here's what I've been doing lately. I joined a group of scientists in 2016. Anton Simon, Dr. Anton Simon and Dr. Tracy Simon are running a tornado research program. Basically, their goal is to use photogrammetry and multi-perspective video to triangulate and get a three-dimensional image of what tornado wind fields are doing right at ground level. So an area where we can't look, we can't see, we have no idea what's going on right at the ground level. Even with our mobile Doppler radar trucks, the beam is still slicing midway up the funnel. So we don't actually know how fast the winds are, where they're actually doing damage. So that's the goal of the project we've been working on. We've been trying since 2016 to get the shot, get our data, get a good case going here. Also in our group is Dr. John Allen. He talked to you guys at the Dupage seminar a couple years ago, I think. He's up in central Michigan now. He chases with us, and he's also in the lab crunching all the numbers for us. So hopefully he'll be getting us some results from our latest data here soon. And then most recently, after the last year's Dupage seminar, where Hank was a speaker, Hank Shima, I said, Hank, you need to come chase with us. You are the guy for getting the tornado shot. We need you on our team. Please join us. And he did. He eagerly jumped on board. So this year we've got Pecos Hank on our team, and there's our whole group assembled. Me with my chase partner, Jennifer Brindley. She's a professional photographer up in Milwaukee, and she's been chasing with me for a number of years. And so yeah, we finally got what we call the dream team. Everybody comes together, and we're finally able to really get out there and chase to our full potential. So yeah, we were super stoked to have Hank join us too this year. So, and here was the day. This was the day that everything clicked and it all came together. So I'm just going to start from the beginning here and walk you through what happened for us this day. This was May 28th, 2019, so last year. I wish I had the high-res local plots. I just have these broad national scale maps. So we're going to pretend we're playing Minecraft here and look at really pixelated images. But hopefully I can walk you through here the setup so it makes sense. But I wish I could show you in high resolution what happened here. But anyway, here's the overall setup. We've got a nice surface low right over central Kansas. We've got an upper level low that's coming out of the Four Corners region there. At the surface, we've got a triple point. West central Kansas, we have a stationary boundary kind of wavy across northeast Kansas into Kansas City. Triple point here is west of Salina, west of Russell, out there somewhere. To the south, a dry line. It's marked as a cold front on here. And a stationary boundary, which is probably a reinforced outflow boundary running way back into Colorado. So that's what we got going on at the surface here, just to give you kind of a broad overview of the synoptic setup here. 500 millibar winds. We've got a trough. We've got a nice burst of energy kicking in, rounding the trough here. So it looks like the stage is set. We've got this dry line, warm front, triple point play. We've got that trough going to initiate off that boundary, send storms into the warm front. Looks like a classic May tornado setup. So we're pretty geeked. And a good strong flow, 70 knots there, rounding that trough axis. And a nice kicking low-level jet here, 850 millibar winds, somewhere between 25 and 40 knots across eastern Kansas here in the warm sector. So good kicking low-level wind shear. So we've got probably a tornado setup here. And just another peek at where that energy on that 500 millibar chart is. So you can see we've got a nice little speed max or a little short wave here coming in, and that's going to set the stage for storm initiation, give us a lot of the speed shear that we need to get things going. Here's mean sea level pressure, just so you can get a feel for the pattern here. There's our nice little low sitting up right here, and just kind of keep in mind of what's going on the top and just immediately behind the low. You know, kind of where those winds start to curl around, so you start getting that northeast surface wind. Just kind of keep that in mind as I go along here, and what's happening with the other parameters in regards to that region. Here's temp and dews at the surface. Very rich moisture coming in the warm sector here. You can see our nice warm front stationary boundary draped across here. But look, out to the west, looks like the moisture is actually wrapping around that low quite a bit. Usually you have a pretty sharp cutoff here and the moisture is east of that surface low. But yeah, it actually had some wrap around there, which was getting our attention quite a bit. So here's Cape, mixed layer Cape. And we have 4,000 joules per kilogram just south of the triple point, just ahead of the dry line, explosive. So storms are going to fire on that cold front dry line. They're going to get really robust, get really going there in that extreme instability, and then hopefully track towards that warm front there and produce tornadoes. At least that's the goal for us as storm chasers. But again, look at that cape. It goes way back west and around the side of the low. So there's a lot of stuff happening up there up in northwest Kansas too. And shear looks great. We've got 50 to 70 knots right across the warm sector there in warm front, and even stronger values there further west where that trough is coming around. Surface to 1 kilometer shear. So I like to look at this when we're looking for tornadoes. So you've got 20 knots of 0 to 1 kilometer shear. That's great for tornadoes, and that's what we have here across much of the warm sector in eastern Kansas, even 30 knots here over Kansas City. That's pretty impressive. So we got some kicking low-level winds here. Effective storm relative helicity. So just a gauge of how much rotation these storms are going to be working with. Our directional wind shear really peaked off to the east over the Kansas City area into Missouri. We've got 300 on the effective SRH. I usually want to see about 200 for a good tornado show, so we've got more than enough here. And yeah, so really impressive values out to the east there where that low-level jet's kicking. Let's go ahead and look at SIGTOR and try and cheat a little bit and figure out where these tornadoes are. Down the dry line, some decent parameter. The hot spot, the largest region of 3, is out along that stationary boundary, that warm front off to the east, and even wrapping around the low again, way off to the northwest. There's a little spot of highlighted area there too. So here's your day 1 convective outlook from the Storm Prediction Center, and they went moderate risk in the morning outlook for this, so 15 hatched. That means they're expecting a big tornado day, and this really gets our attention. Wow, this is going to be a big moderate risk day. It's going to be lots of tornadoes. And so where is our target, right? Pretty much textbook, right? We're going to look for initiation here off the dry line. Storms are going to track northeast. When they bump that warm front, they're going to spin up a tornado for us. So Lawrence, Kansas, right? It's a slam dunk. We said, nope, we're not going to Lawrence, Kansas. Yes?
Do you want us to write this down?
You can write whatever you want. This will not be on the quiz. So I know Paul might put it on the quiz. I'm not going to put it on the quiz. So yeah, whatever you want to take notes of, go for it. So, anyway, we decided, no, we're not going to play the normal target. We are going to play way out west in the 2%. So, and why are we doing that? Because it looks so good off to the east there. And here are the plots that I kind of want to show you that nudged us away from the popular conventional target. So this is LCL heights. Roughly, it's going to be how high the bottom of your storm is off the ground. So I usually want to see this at 1,000. Lower is better for tornadoes, but when it gets too low, you actually can't see the tornadoes anymore because they get rain wrapped and there's really scuddy and grungy. It's hard to see, and if the terrain's bad, forget about it. So I want these to be in a nice sweet spot at around 1,000. Out here in eastern Kansas, where it's really saturated, LCL is between 750 and 500. It's really low. A little worried about the chaseability of those storms. Drier air out west really had this nice nosy of drier air punching in here to the west, right under that surface low. So getting a much better LCL value there that I'd like to see. This one was really, really big for us. This is precipitable water. How much water is in the column of the atmosphere that can be squeezed into rain, right? And so I'm getting values of almost 2 inches out here in eastern Kansas into Missouri. And so that's a ton of water up in the atmosphere, and that's going to be dumped out of the storm here. We're going to have very, very rainy storms to the east. So I do not like seeing a high PWatt like this at all. But looking out west, ooh, much closer to 1 out there. So that's definitely getting my attention too. here are 300 millibar winds, so up in the jet stream, right? So we're looking for that upper level wind shear, venting for our storm, those anvil level winds. And what do we got here? All of the energy is way out west. It's lagging behind the warm sector. So our storm is coming off the dry line. It's going to start moving into lesser winds. So what does that mean? We've got a ton of CAPE. We've got a ton of precipitable water in this column. We've got very low LCLs. We don't have a lot of venting aloft. What kind of storm are we going to wind up with in that kind of environment? Any guesses? HP, absolutely. So we are anticipating a high precipitation storm mode out east. So we said, no good. I don't want to chase that kind of storm. So this was the kicker for us. If you've been to my Dupage seminar talks, I talked about my secret weapons. On the mesoscale analysis, you can pull this up. This is 0 to 3 kilometer CAPE. So the atmospheric instability in the lowest layers of the atmosphere. If you have a lot of this, it's good for tornadoes. Tornadoes need 0 to 3 kilometer CAPE. Where is it peaked? We have a big, big bubble right on and actually behind the surface low. And what's really crazy about behind the surface low is you have a kicking northeast wind back there. And there's often a ton of surface vorticity. So when you have this combination of really robust instability in the low levels and really, really strong vorticity, that screams tornado to me. So I saw this plot and I said, yeah, let's not go east. These storms are actually moving into a less favorable environment in terms of low-level instability. Still a lot here over Lawrence in the Kansas City area, more than enough for a tornado. But this is really getting my attention. Where these blue rings and these red rings meet, way out here in north central Kansas, I said, that's our target. Let's do it. So, and just logistically speaking, I'll try to talk to the other screen too. Like we want to get a tornado that we can get a shot of. That's our goal. So it's not just enough to forecast where the tornadoes are going to be. How chaseable are these going to be? So going out to eastern Kansas, this is what I am imagining. Last year we had a high risk over Oklahoma. They went 45 hatched on the day one outlook, which is huge. You're expecting a big day. And the parameters that day were pretty iffy. We wound up with really gray, hazy, low contrast skies. And this is a tornado. Can you see it? So this is not what we want. This is a crappy tornado. And here's the other problem is this is an entire line of storm chasers, and we are going 35, 40 miles an hour. Well, this thing is saying, bye-bye, I'll see you later. So it's just sailing away, and we're all stuck in what Tim Marshall calls the conga line. So we're thinking, okay, where is the conga line going to be? Where is the crappy storm mode going to be? And that's going to be eastern Kansas, because everyone's going to be playing that big moderate risk where it's 15 hatched, and where the skies are really gray and soupy. So we said, nope, we're not going there. We're playing the secondary target way out west. So here we are, Beloit, Kansas, chilling in a park at 4 o'clock in the afternoon. When we arrived in Beloit, we had surface temp, I think was about 78 degrees, and we had a 70-degree dew point with a northeast surface wind. So when we got out of the car and felt that, like it blew my mind. Normally when the wind starts to back from southerly up to easterly and then northeasterly, you're on the cool side of the boundary. Okay, so you're losing your CAPE, you're losing that energy you need for your tornado. Great directional wind shear, but all the CAPEs down south where those winds are actually out of the south. But here in Beloit, we had both. Northeast wind and it's unstable. Wow, it screamed tornado to me. So we were super, super geeked to play this setup. And we're about an hour out from the show now. So, and here we go. Storms erupted and tornado warnings, and we're off. And this was the first storm of the day that we passed. Nice meso here. Great structure. I wanted to stay and chase this thing. There's another storm way down here that's producing. So luckily, people in our group came together and we all clicked as a team and we said, nope, we can't keep up with this. Let it go. Get the producing storm. So almost missed the tornado show, but we kept going and we arrived to this site. So here's our storm that we wound up intercepting, absolutely gigantic supercell. This is a super wide angle shot, so you're looking at the entire sky here. This mesocyclone is several miles wide. So this is a normal sized tornado coming out of the bottom of it here. We're way back. So big tornado coming out of an unusual spot. I usually want to see it parked kind of in the center of the meso. Why is it way out there? And this thing is absolutely gigantic. As we approached, there was just this bewildering array of vortices under this thing. It's actually really intimidating because on the approach, didn't have bearings on where the tornado should be. I just saw a gigantic mesocyclone spanning the whole horizon. And there was a funnel here, another funnel there, and a third funnel over there. So there were tornadoes coming out of this thing left and right. I didn't have my bearings. It's kind of intimidating. So I thought I was really uneasy on the approach here. So, but yeah, then just a crazy alien mass of tornadoes and funnels on this storm. So some really freaky, weird stuff. This looked like it was on the southern rim of the mesocyclone, but then way out to the east, there was this thing, another tornado, and you can see it looks like a tiny little occluded updraft here, but then there's this snaky tube running all the way across here. At first I thought it was like a horizontal vortex arch, a toroidal thing, you know, where you have an anticyclonic tornado and a cyclonic pair, and this arch connects them. But what we actually think is this is just the updraft tube from this tornado, and for some reason it's grotesquely distended out from the storm. So really bizarre, otherworldly behavior on this storm, seeing these updraft tubes. There's actually an updraft tube that's coming way up out of this one too. It's kind of hard to make out with the contrast here. But yeah, here's a video of these two tornadoes in progress here. So super, super pretty. We don't yet have our research case though, because we want to get in a nice close shot of what's going on underneath these funnel clouds here. So we said, let's go south. Let's get in there for the shot. So we stopped right next to a little farmstead. And then the tornadoes finally consolidated. Now I had my bearings, tornadoes right parked in the middle of the mesocyclone where it should be now, and that's when it really took off. It's underneath the main updraft of the supercell. So much bigger, much more robust tornado now. All of these little tendrils spinning around underneath the funnel here. You can see the low-level jets and the mist kicking through, and some of the outer circulation spiraling around it. So finally starting to get a good shot. Things are looking really promising. We're just letting this tornado come to us now. And in fact, it was coming right at us. So we had to actually duck south to get out of the way of it, turned around, and this is what we saw when we turned around. That farm that we were just parked at, here it is getting struck by this tornado as it impacts. Luckily, this is just an outbuilding. It's not a house or anything. But this is an entire barn right here in the air flying apart. And the crazy thing about this is here's the funnel. So you've got suction vortices and where the funnel touches the ground over here. Look how far ahead that barn is flying to pieces ahead of that tornado. So that makes me really uneasy. So sometimes I feel like I can get close to a tornado because the funnel's small and it's over there. But these winds, they extend way out from these tornadoes sometimes. So you've got to really watch out for that. So this was the shot. This is what we've been trying for 3 years to get. That's Pecos Hank. We're in the vehicle, and Anton and Tracy are behind us. And we have all three teams shooting this parade of suction vortices and the debris as this thing crosses the road immediately in front of us. So now we can take these 3 shots, 3 different angles, triangulate them, and we can actually now, hopefully, when John Allen crunches the numbers, get wind speed measurement readings as that tornado crossed the road there in front of us. Thanks. So yeah, this was our big catch, and finally we pulled it off. So all 3 teams coming together, clicking, and from the forecast to sticking to our target to Hank stepping up and saying we should intercept this storm here and here and here. So everyone came together and we had a great chase and pulled it off. We drove up to the farm. Hank immediately got out and ran into the farm to see if there was anybody in there that needed our help, because the last thing we want to see as storm chasers is people get impacted and hurt and killed by these things. We want all of our tornadoes to be out here in the field. We don't want to see any sort of human impact at all with these tornadoes. And almost all of them are out in the middle of nowhere where this doesn't happen. Luckily, no one was home, and it turned out that just barns were hit. So the houses were actually fine on that farm. So good news all around. We got a data set. There were no casualties on this tornado. 24-mile-long path length, half a mile wide. So, and an EF2, pretty significant tornado. So, yeah. And just, this is a really wide shot of when we were looking at those tendrils here, but the structure here is really kind of crazy. You have this barber pole updraft above it, and then like, check out this cool wave coming off the back side of that mesocyclone. So, some sort of horizontal roll or something, like almost like a wingtip vortex or something. So, just really neat stuff. Would love to know what is actually going on in this storm. So, poor SPC, kind of had a bad day, kind of dropped the ball. This was our storm here. So it actually started producing outside of the 2%. And this was our main target way out here on the edge of the outlook area. There was another supercell that produced, and they nailed that one finally. But yeah, we actually did not get a tornado watch at our target until 15 minutes after the first tornado. So it's just kind of crazy. Like, it was like they weren't paying attention to that corner of the day. But to me, that little corner of Kansas, it just screamed tornadoes. So that's the kind of stuff I'm looking for, is that secondary target where we can get a pretty tornado out in the middle of nowhere. So it wasn't all good news for everybody that day. Unfortunately, while we were chasing this tornado, another tornado near the Lawrence, Kansas area impacted a commercial storm chasing tour group. We found out that 2 of their vans had been rolled by a tornado and that there were injuries.
No casualties?
Well, yeah, there were injuries. Nobody died, though, so that was good. So these were the initial reports out of the accident. It was a fluke spin-up tornado. It was a satellite 2 miles south of the main mesocyclone, and that 2 vans had been hit by this relatively small tornado. Had the vans been just positioned a little bit further down the road, it probably would have missed. And there were a few minor injuries. So I said, wow, that's pretty crazy. It's just really, really bad luck. The National Weather Service conducted really, really detailed damage surveys of these tornadoes. And what happened was there was a big EF4 that wound up tracking south of Lawrence, Kansas. That's the track way up on the top here. And then there was a long track EF2 that preceded that tornado. And what looked like happened was the EF2 actually merged into the developing EF4. So kind of an unusual tornado situation there, where you've got merging tornadoes on these very interesting looking tracks. And people said, Skip, you should look into this, what happened to this tour group. And I thought it was a pretty open and closed case. It probably got a little too close, and there was this freak tornado that wound up hitting them, just really bad luck. Here's the site of the accident where the tour group got struck. And so I saw this and I said, whoa, something else is happening here, something pretty crazy. It looks like this is actually a long track tornado that they got hit by, and actually doing some pretty significant EF2 damage here. And check out these weird shapes in the path here. There's like these unusual lobes in the damage path of the tornado. I'm not sure what that is. I didn't talk to the NWS folks to see why they put that shape there. What I'm guessing is there's an inflow jet into the tornado here. There's surges of wind that are feeding the tornado, and that's where the tornado ramps up. So we get our most intense damage here, and there's probably an inflow jet here feeding this tornado and making it ramp up right there. That's where the tour group got hit. So I said, this is a really unusual and interesting case with a merger, a long track tornado, and an accident here. I was really curious to figure out what would happen here. It turns out that none of these initial claims were true. Instead of a fluke spin-up tornado, we had a significant EF2 with an 11-mile path length. This turned out to be the main tornado. It was pendant to a long-duration mesocyclone. It was not a satellite. It's a pretty wide tornado, 300 yards wide at its widest, and it hit all 4 vans in this tour group. 2 of the vans got rolled, but all of those vans were in the tornado, according to the damage survey and the videos from in those vans. So really pretty significant accident here. And the initial reports of the injuries were really, really underestimated. 12 people went to the hospital. There were broken bones. One of the clients was airlifted to Kansas City with a broken neck. But fortunately, everybody has made a full recovery as far as I can tell. So I started digging into this, and I thought, this needs to be looked at more. We need to figure out what went wrong here, and hopefully help chasers not fall into this same situation again, so that we can hopefully avoid an accident like this. I contacted several of the clients that were on that tour. Do you have photos? Do you have videos? Where were you that day? And after, this was probably a 5-month-long project, hundreds if not thousands of hours of work went into this. I produced a video presentation about what happened on May 28th and what went wrong that day. So I'll cover a little bit of that here tonight, but if you want to see the full thing, it's up on YouTube. I go over in exhaustive detail everything that happened that day and what the storm looked like and all of the structure here. But in a nutshell, here's what the tour group did. They started east of a little town called Overbrook, Kansas. They stopped in front of a very large, high precipitation supercell. You can see here's where the mesocyclone and hook echo would be. It's coming up there, up to there. And this here is the tornado track of the tornado that impacts them. You'll see the tornado appear on the map animated. But here's the mesocyclone. These are tornado warnings. The tour group moves east to stay ahead of that storm. Tornado forms behind them as they're driving down the highway. They can't see it. It's very heavily rain-wrapped inside of this high precipitation supercell. They turn north on the first paved road that they can find, hoping to get a view of a tornado somewhere in that storm. They turn around, hoping to get back to that highway, and then they're struck by this tornado, buried deep within the core of that supercell. Here is the velocity, storm relative velocity. You can see the red and green here indicating rotation in the mesocyclone. And then as that tornado forms, you'll see a much more intense velocity couplet associated with that tornado here. So here it goes, and that tornado peaks as it crosses, or the velocity couplet peaks as it crosses the highway there. That tornado was actually close to peak intensity when it hit the tour group. So, but weirdly, the velocity couplet is actually very difficult to see during that time. So I think a lot of chasers had problems identifying that specific couplet at the moment. But anyway, here's basically what happened is this tour group started probably up north in the Topeka area, came south as storms were firing on that dry line cold front, and then headed off this line of storms east of this town of Overbrook here. You can see a big V-shaped forward flank on that supercell. And then this is what would normally look like a hook echo on a normal storm closer to the radar. So a more classic supercell. But you can see there's a little weak echo region here, almost like a donut hole in the storm. So that donut hole is where the tornado is going to be, or where your mesocyclone is going to be. So this is the radar software the tour group was using at the time. It turns out that they were probably aware that there was a velocity couplet and a potential tornado in there. So talking to the clients, it looked like they knew that there was probably going to be a tornado in the storm, and they were actively trying to identify it at the time here. So, but pretty difficult to see. You have to know what you're looking for. This is the velocity couplet. The tour group would have been right about here when they were chasing this storm. So yeah, and really well warned. So all of this is coming together to me, and I'm now trying to figure out why. How does this happen? This tour group is led by extremely experienced, exceptionally well-known, and highly regarded storm chasers. We have a great big storm. It's well-warned. This is the tornado warning, this polygon here. There's 20 minutes of lead time from the accident site to when they got impacted here, from when the warning was issued. And the forecast track of the tornado was really well identified. They used rotation in the mesocyclone to identify where the tornado would most likely form, gave them several minutes of lead time before the tornado finally formed here. And then that tornado tracked right along this forecast trajectory. So inside of the tornado warning, they encode the direction and the course of the tornado. And that tornado deviated only a half mile from the actual forecast path of that tornado. So to me, this was a well-forecasted anticipated tornado. And I was a little baffled as to why such exceptionally experienced storm chasers were falling victim to this. Luckily, we had visuals of the storm itself to kind of figure out what this storm looked like and maybe what storm chasers were thinking at the time, because that's the big mystery to me. Here's the tour group. They're a couple miles east of this tornado, right at the ball at the end of that hook echo. That little blue arrow is another storm chaser. This is his view to the west, so this is the actual storm structure that they're seeing at the time. That's the tour group driving up here. And so knowing the position of this chaser and where the tornado was at that time, according to the radar and the damage survey, we can actually plot on the video where that tornado would have been. So this is kind of where the investigative mode stepped in here to figure out what went wrong on this chase, what mistakes were made, hopefully give some recommendations on how to correct them. But you can see the tornado is buried in this very heavy area of precipitation, this bowing rear flank downdraft gust front. And off to the north here, there's a dark cloud base, what I believe is the supercell's inflow band here. And to me, this is pretty much textbook high precipitation supercell structure. This big ball of rain in the rear flank of the storm, that is rain wrapping around the storm's mesocyclone. These spiraling rain bands are what chasers like to call the bear's cage. Those spiraling rain bands form the bars of the cage. Embedded inside of that cage is the tornado. The tornado is the bear. So on an HP supercell, they're often completely rain wrapped and impossible to see. But one of the things I try to do at Dupage whenever I get the chance to speak is offer visual cues, structure identification to help storm chasers identify these parts of the storm and infer where the tornado is going to be. So even though we can't see the tornado, to me there is great supercell structure still visible here. We have a bowing RFD gust front. The updraft base is ahead of that gust front here, and it makes this horseshoe shape, a bowing C, a backwards C. And the tornado is usually at the top or north side of that. And then off to the north, there's an inflow band feeding into this storm here. It's moving right to left into this region. And to me, that just points the way. It points at where the tornado is going to be. If I can see this kind of structure here, it gives me great bearings on where that tornado might be. So again, my goal, my hope is that storm chasers will see a site like this, and they'll have their bearings on this storm. They'll say, hey, this is a supercell. I can see the rear flank gust front here. I can see the inflow band. You can even see the clouds, how they spiral. This whole mesocyclone above this base here, these clouds just spiral around it. That's where the broad scale rotation is. And my hope is that chasers see this and they said, yeah, there's a tornado. And if there's a tornado, it's probably right in here. So at a glance, my hope is that's what chasers do. At some point, Silver Lining Tours, the group that was hit, they got north of that storm feature into what I like to call the inflow notch. They went north of the path of the tornado, and they turned around. Maybe they didn't see a tornado in there. Maybe they were trying to reposition. Maybe they thought that this was a dangerous part of the storm. But for whatever reason, they turned around and decided to head back to Highway 56 here. They still can't see the tornado in progress, now 1.5 miles to their southwest. And this was their view at the time they turned around. This was shot by one of the clients. If you remember that storm structure from the last picture I showed, this is your dark inflow band feeding into the storm. This is the bear's cage. It's this round circular region of streaky rain. These rain bands are spiraling and wrapping around the circulation. So when I see this, it just screams, this is the danger area. Watch out. And unfortunately, the tour group turned around and wound up driving directly into that area. So again, my hope is that chasers recognize that this is the most dangerous part of the storm. This is the structure you need to be looking for and not enter that. So it was about a minute or two later that they were impacted by the tornado that was rain wrapped inside of that region. There's a video of the impact on YouTube. I didn't put it in this presentation, but if you watch my presentation or watch Jeff Lieberman's, the actual raw video is up on YouTube. You can go and see the impact. But totally rain wrapped. They didn't know it was there until basically it was right on top of them. So, and so chasers were kind of fixated on why did they turn around, what was going through their heads, what what kind of was the reasoning here behind this. One of the things I often heard cited was there was an area of rotation, a large mesocyclone off to the north. And this tour group was turned around to avoid that area of rotation. You can see this big area of red and green. If you track it from frame to frame for several minutes, it looks like it was tracking from west to east and then makes this abrupt left turn and goes to the northeast. The tour group and others are claiming that they turned around avoiding this rotation because this rotation goes on to produce the much larger Lawrence EF4 tornado. It turns out that both tornadoes followed a really straight line. The tornado track of the EF2 and the following EF4 were almost on a very linear rail. So it was like something else was going on here. There's a steady state path for both of these tornadoes. And I think what's happening is this is the actual track of the storm's mesocyclone. The tour group thought they were south of the mesocyclone. They were actually north of the main tornado-producing region of the storm. These are gusts in the velocity data feeding into this region. So we have a big inflow surge here. We have a big rear flank downdraft surge here. And I think that's instead what's going on with this velocity data, rather than there being a mesocyclone to the north. So again, this is the area in question. Chasers looking at this much more prominent area on the lower resolution radar. They're saying, hey, here's the mesocyclone. There's rotation in there. That has my attention. Some of them can't make out this small couplet here, which is where the actual tornado is. So they're confused. They're thinking that this is the actual mesocyclone off to the northwest. This is what they're looking at as the primary tornado-producing region of the storm. And it turns out that this was probably a really critical mistake and a misinterpretation of both visual storm structure and the radar data. So one of the things I've done since this presentation is taken a much closer look at this part of the storm, because chasers are still saying that this is a mesocyclone. I'm under the impression that this is an inflow band. Storm chaser Quincy Vagel has this shot at 2259 looking northwest, what we're calling the mesocyclone here, but I've plotted it on top of the actual velocity data here at that time. Quincy's running a GoPro. It has a 90-degree field of view. So using Google Maps, I can plot his exact location. I can plot the actual viewing frustrum on top of this velocity data to see what actual part of the storm he's looking at. So the center line of his camera is actually looking across the most intense inflow winds in the storm. So he's not looking at the center of a velocity couplet like down here. He's looking at the inflow half of a mesocyclone. So to me, that's the big takeaway lesson here is Quincy is not looking at the mesocyclone. He's looking at the inflow notch, the inflow portion of this storm. So this is not the area where you would expect the big tornado to come out of. It would be further south here, where this rear flank downdraft is meeting this inflow here. So I think this is pretty significant and important to point out that chasers are misidentifying storm structure and they're misidentifying the radar. So this is something that we need to work with chasers to help them correct. How do you find rotation on radar? You want to look for where the red and the green meet, right? The red pixels and the green pixels, that's where stuff is spinning. But it turns out that the orientation of those red and green pixels is important too. So if you draw a line between these two pixels, it should parallel the radar beam. And that indicates rotation because your winds are flowing around in a circle around this velocity couplet. So what's going on to the northwest here, where chasers are calling this the meso, is this line is not parallel to the beam. It's at an angle. There is some rotation there, but there's also significant convergence here. So what this is telling me here is this is actually a part of the storm where you'd have converging winds curling into the north side of the mesocyclone. We'd call it an inflow band. The storm pulls this inflow band in and it kind of feeds off of this area, a convergent inflow band area off to the north. And it's being mistaken for a large primary mesocyclone. Chasers are taking their escape routes to avoid it. They're looking for tornadoes there. And unbeknownst to them, the danger area is to their south where the actual tornado is, and they wind up driving directly into it. So here's kind of what's going on at the surface. At the lowest tilt of radar, we have a velocity couplet associated with the tornado, a tornado vortex signature, very small, less than 1 kilometer in size. Off to the north, we have this convergence rotation area on the inflow band. But I think chasers are kind of overlooking the bigger picture here. Because if you go up a couple degrees on the radar beam, you get a much better picture of what the actual mesocyclone of the storm is doing. So here we have a very large area of rotation, 10 kilometers in diameter. So this is a big, big storm. There's a mesocyclone that's 6 miles wide here. So chasers are worried about ducking and dodging these smaller, what I would probably call tornado cyclone scale features or tornado vortex signatures, but they're actually inside of and in the immediate path of a much larger mid-level mesocyclone. So I think that broader picture is being overlooked here in terms of what's going on in the storm. I plotted the rotation of this storm here, stepping backwards from the Lawrence EF4 and then going back all the way from before the EF2 here to figure out where are the rotation signatures, where are the convergence signatures on this supercell, what's going on here. Here's the pattern that emerged from this data. There was a track of rotation from southwest to northeast. And then before each tornado started to the north, there was a strong area of convergence that became more focused convergence and rotation, and finally tight rotation. When it merged into the track, that's where we had each tornado spin up. So pretty neat pattern. What's causing that? I don't know. This is speculation on my part, but what I think is happening here is the supercell's main updraft is tracking pretty much in a straight line. And then before each tornado, the storm is taking a deep breath. Basically, there's a big inflow surge here on the inflow band, and the storm draws that in as focused rotation along the inflow band. That inflow band merges with the northeast moving supercell, and when it does, that's when the tornado spins up. So we see this pattern before each tornado forms. Probably a supercell cycle, but there's one main mid-level mesocyclone tracking along this line. So pretty neat. And it's kind of cool is this rotation, these tornadoes had a little left hook right at the start of their path. We saw that with the EF4 that formed up here, but it was really neat to see it on the EF2. So the same pattern, both tornadoes. So kind of a glimpse into what the structure on the supercell is doing. So looking for other analogs in the literature, there's a paper in the AMS journals you can look up online. I think it's a really good case study at what might have been going on inside of the storm here if you're interested in some of the more nitty-gritty meteorological details. But we're seeing basically the same pattern. This is the May 24, 2011 El Reno, Oklahoma supercell. So this produced an EF5 tornado. It was actually a small tornado merger with this event, just like we saw on the Lawrence-Linwood, Kansas storm from May 28th. So, and the velocity pattern is very consistent, similar to this other storm. Convergent inflow band on the north, and then occluded behind the rear flank gust front is this velocity couplet here. So we have the EF5 in progress here. We have an area of convergence off to the north, and then that becomes more focused as rotation as these frames progress here. And eventually we get a merger of two velocity couplets. So pretty neat to see this pattern show up in other places here. So storm chasers on this storm, very similar structure. It's really tough to see with the lighting here, but there was a great big rear flank downdraft core, inflow band off to the north, very similar structure to what we saw with the tour group here. The chaser on this did an amazing job spotting the structure though. So I was actually really happy to see how he's reporting this. I correctly identified this as the rear flank downdraft, this as an inflow band off to the north. And he says, I've seen funnels form on inflow bands like this before, and indeed that's what happens here. Here's his video shot. This is an inflow band feeding right to left into the storm's mesocyclone here. This is a developing tornado. And you can see these streaky bands of rain.
This is like the worst place on earth to be.
that's like the rear flank downdraft wrapping around this tornado. That's the Bear's cage. So this tornado is coming in from the north, moving into the Bear's cage region here. So yeah, he has these great little notes here, and he suspects, without being able to see that there's a tornado, there is an EF5 in this rain. He can't see it. But just looking at the structure here, the inflow band, the motion of that funnel cloud, he's deducing, hey, this thing's moving more like a satellite. I think there's actually something much bigger in the rain here, and he's right. The rain clears a little bit, and this passes just to his south.
I think that's a tornado.
So EF5 tornado.
It's quite loud.
And actually the other little tornado that he saw form, you can see it coming around the back edge here. It's a satellite now orbiting into the main circulation. What we saw on the velocity scan there, these couplets merging.
Holy crap.
So the main takeaway here is that
All right.
he was able to identify the structure he was looking at. He didn't freak out and say, hey, that tornado's to my west. I'm going to get south and get out of the way of this thing. Because if he did, he would have driven straight into this thing, a much larger, much more intense EF5. He could have been killed. So my hope is that we can give chasers the tools to be able to identify the structure on these kinds of storms. Say, hey, you're looking at an inflow band. You're not looking at the mesocyclone. This large circular region of spiraling rain bands, that is the Bear's cage. That is where the mesocyclone is operating. That is where the main tornado is going to be located, okay? So don't take your escape route into that part of the storm. It's extremely dangerous. So another person who has been studying that May 24, 2011 storm intensely, Dr. Lee Orff up in UW-Madison, he produces these amazing supercomputer visualizations of these storms. So if you haven't seen Dr. Lee's work, go on YouTube as soon as you get a chance and pull up these videos. They are super cool to see. Hank has been collaborating with Dr. Lee. He's giving him actual storm shots of his own and comparing them to the models that Dr. Lee is using, and it's amazing. The two sync up perfectly, and you can really see the real-world structure reflected in these supercomputer
and yes,
physics
our simulations of this particular storm, May 24th, 2011, in all cases, when you trace the air with trajectories, when you drop these little parcels, you put them in front of the storm, they'll enter the updraft, but they won't go into the tornado. The parcels that you drop in the cold pool, especially certain regions of it, they take a beeline right for the tornado and get pulled up into the tornado circulation. Now, the fact that we're not seeing any air coming from the warm side to feed the tornado is an interesting result, and if it turns out to be
Dr.
true,
Lee
I think
has
it's an
cracked the
important
code.
result.
Near a supercell, there are many fascinating
And Hank
things
has proof
observed
of it.
that often
And this is the
overshadow
pattern that's at work
the
on these
inflow band.
storms.
Your animations are suggesting there's a lot more to the inflow tail than just a thin cloud streaming into the mesocyclone.
Yes. First of all, the fact that it produces a tail cloud is good because tail clouds are common in supercells along the forward flank. They're not always there, but that interface is where a bunch of interesting things can happen. Let me talk about a couple of the things we've found in our simulation that I don't think has been seen in Mother Nature. We have found very interesting organization of vorticity in the cold pool of our simulated storm. And one of the features we've identified, or at least we've given it a name, is called a streamwise vorticity current. And this is sort of you could call a helically flowing tube of air. It's sort of tilted into the storm's updraft, where it becomes rotating cyclonically in the same direction as the air in the mesocyclone and any subsequent cyclonic tornado. So this feature is one that shows up in our simulations of the 24 May 2011 environment in all the simulations we've done. So one of the tools that we have used with our simulation is to place these air parcels sort of like chaff. You just release them every second or so in a certain region of the storm to see where that air will go. We'll follow the temperature, the humidity, the precipitation, and the pressure along the path of the parcel and the forces acting on it. And that's a very powerful method for trying to untangle the physics of what's going on.
So check out this
We
pattern
see
here.
dozens and
these
dozens
little guys
of these
feeding
little
in.
vortices along the forward flank that merge together, that sometimes just get assimilated into the cyclonic flow of the main tornado. If they're anticyclonic, they get twisted around the tornado's periphery and spun and stretched and tilted and all sorts of cool stuff. I know that some observational studies by Bluestein and Werman and some of those guys have shown that these vortices are out there. You can't see them with the naked eye. Sometimes they'll spin up some dust if you're lucky, but oftentimes there's all these vortices in the air that we cannot see with our eye. I'm thinking of creative ways to use videography like what you produce, Hank. Are there ways for us to get some more information from the video? If you're lucky enough to get something kicked up, some dust and all that, then you can start to look at the full three-dimensional wind field.
When you're underneath the storm, and let's say it starts off and it's got kind of a linear mode, and then you see that RFD start to march around, it's usually go time. And that's when you position, and then it won't be long.
These
often
bands wrapping
when
around
the
are
show
what
really
I'm hoping
starts,
chasers
which is
identify.
why we
That's
generally
the Bears
think that
cage
this
at work
RFD
here.
is a mechanism in tornado genesis, but it might be all of these things working together that are also driving the RFD. It could be the SVC, like you say, that's driving the RFD in sync, coming around perhaps.
Perhaps. You raise a very good point. It's a matter of correlation versus causation. I mean, this is still a leading theory of tornado genesis, is that a downdraft impinges the ground, it spreads out like a downburst does, it forces convergence of existing vorticity, and once you get it stretched, boom, there's your tornado. Now, even if the RFD is an important source of tornado genesis, I don't see how downdrafts in the RFD can maintain a tornado, because the RFD is a very sporadic place. It's not like there's this constant stream of downward air going down nice and smooth. It's much more transient, and these downdrafts happen all over the place in their RFD. So perhaps there's something else going on that is causing the RFD behavior and causing the tornado. So the RFD is more of a symptom than a cause. And again, I don't know that I'm right.
All the features move and behave like the organelles, if you will, I've seen in the field. The rolling plumes of the updraft, the tumbling mammatus in the back
compared to
shear
the
region,
actual simulations.
wall cloud appearance.
Dr. Lee is making this like side-by-side comparison to me is absolutely mind-blowing.
And the tail clouds streaming in along the forward flank.
These are the same patterns we're seeing on that May 28th storm
The laminar,
that hit the storm
wind-sculpted region of the
chasers.
mesocyclone and the demarcation into the turbulent region.
I think Dr. Lee has actually kind of figured out the actual mechanisms behind it. So I just thought it was really cool and kind of important to point this out, that these are the same processes
Tornado.
at work under
It's
this
multiple
storm.
vortices. The horizontal vortices riding up the tornado. The way the RFD wraps around the tornado and sometimes clears and wraps again.
Again, same patterns we're seeing on this storm that impacted chasers. So I think this is just a great visualization of how these processes work and what they look like. So my hope is chasers can identify these kinds of things, these shots, and identify these patterns here. This inflow band off to the north, what chasers thought is a mesocyclone, is probably closely associated with Dr. Lee's streamwise vorticity current. So you're getting vorticity that's being funneled into this large donut-shaped mesocyclone here. It makes this very nice comma head pattern, and that is where your tornado is going to form, is right at the end of this comma head pattern. So you can see this pattern persist through the life of this storm. The entire length of the EF2, the start of the EF4, and then well into the EF4 here. For a long time, we just have this very consistent comma head pattern. And what I think you're seeing here is the actual structure of the mesocyclone reflected in the reflectivity data here. So, and again, this inflow band off to the north, I think is playing probably a pretty significant role in the tornado formation itself, but it's also a great landmark for spotters and chasers to get their bearings on this storm and figure out where they are and where the tornado is. So here's the old school conceptual model, Lemon and Doswell, 1979, and this is great, still valid today. The tornado forms at the end of an occluded gust front here, where the rear flank downdraft meets the forward flank downdraft. I think it's kind of stuck in a lot of chasers and spotters' heads that the rear flank downdraft is south of the tornado. The tornado is not buried in this RFD. But I want to try to stress that when you're working with these giant HP supercells, these are the most dangerous types of storms that there are. That tornado is often buried really deep inside of that RFD. This is where you should expect it on such a storm. As much as 3 miles behind that big circular green precipitation core in the rear flank downdraft, that's where you're going to find the tornadoes on these storms. Not up here in the clear air under the inflow notch. On a big HP storm, that tornado is often buried right down there at the bottom of that hook. So, and I think chasers might be overlooking that, expecting maybe there's going to be a tornado up here, and disregarding this as just rainy rear flank downdraft. So to me, that's one of the more important takeaway lessons from this event. So again, it's really tough to look at velocity data in the field and say, oh, there's a convergent inflow band up here, and where's the mid-level mesocyclone? No, I don't want chasers to be doing that. My hope is that chasers see this scene here, and they say, hey, I've got good bearings on supercell structure. Here's my rear flank downdraft gust front. The inflow notch is here. I know where I am relative to where the tornado is going to be. I'm not relying on the radar data for my safety, because I think that's going to get you in a lot of trouble, saying, okay, here's the Bear's Cage region where that big circular core is, the gust front, the inflow band. Maybe I need to get a few more miles spacing here as a safer alternative for my chase route. A more risky maneuver would be to cut north across that path now, because it's kind of a race to get in front of that thing. So again, going off of these visuals rather than your radar data to get your bearings, here's that Bear's Cage just coming in, looming over these chasers. The tour group now at this position here in front of this storm, I'm, as a chaser, thinking, hey, maybe this is a good time to abort, turn around, and head back before I get run over by this thing. A much more dangerous trajectory would be to keep going north into the path of this thing. But they actually make it. They're in ahead of the Bear's Cage region here now, looking south. You can see it's actually crossing the road here. And to me, this is one of the most critical safety lessons that we've learned while storm chasing. This is what's getting people hurt and killed out there, is it's this moment here where they decide, I'm in a dangerous spot, I need to take my escape route. And what they're doing is they're trying to head back south to clear air or east out ahead of the storm. And what they're doing is they're crossing the immediate path of the tornado and the Bear's Cage region. And in doing so, they're racing this freight train across the tracks, and they're getting hit by it. So you can get away with this on a small tornado, but a big, giant HP like this, people are getting run over, people are getting hurt and killed. So this is what we saw on the El Reno storm. We're still seeing it. This is why I still stress this safety lesson here, is don't go south across the path of that region. Take a moment to see where it is visually. Don't cross the path. So, and again, these are my big safety lessons here, is look for that visual structure, identify the dangerous parts of the storm, and keep a safe escape route that does not cross the path. The other big takeaway lesson is, if you lose your situational awareness, you also need to take that escape route away from the storm. So in my safety videos and at the Dupage seminar, this is what I've been preaching over and over again, because I still see storm chasers falling victim to this. I'll just wrap it up with some safety stats I tried to come up with. How dangerous is storm chasing? Dan Robinson put together this chart of storm chaser fatalities in the last several years here. I think he did a great job here. It's really interesting. Since 2005, when we started really seeing more, there have been 7 driving-related fatalities with chasing. And so here's kind of the accident rate per year that we're seeing here. What's cool about this is we can compare this to the national average of 11.7, and we can use these numbers to actually estimate how many chasers are out there on the road. So if storm chasers are kind of paralleling the national average accident rate, I'm guessing there's probably about 4,000 chasers out operating on the road. So it's a crude estimate, but it's probably within an order of magnitude, I'm guessing. And we can use that, adding in the storm-related fatalities. It turns out there's been 5 over the years, bringing us to a total number of 12. We can actually figure out how dangerous is storm chasing compared to other activities. And I was actually kind of surprised by these numbers. They might be a little bit high. Somebody needs to check my math on this. But according to these numbers, storm chasing is actually quite dangerous. More dangerous than scuba diving, way more dangerous than skydiving and rock climbing, which turns out are actually relatively safe. It's actually much more dangerous driving down the road on any given day than it is to go skydiving, believe it or not. It seems like a scary activity, but the accidents are pretty infrequent. Turns out jogging is quite dangerous. You wouldn't think so, but like people get hit by cars all the time. So climbing Mount Everest, okay, there's your high end, very, very dangerous. Paragliding, very dangerous. But yeah, storm chasing, it's up there on the rankings. I was surprised to see this, to be honest. So I think storm chaser safety is a very important topic. If you're going to dedicate your life to it like I'm doing, it's something that we need to figure out and pay attention to and figure out what mistakes chasers are making. This is the 2013 El Reno storm. This is Mike Bettis. He's about 3 minutes from getting rolled by this tornado. His vehicle is going to get smashed. He's going to have people in his group injured. So, and the crazy thing to me is he identifies the tornado. He identifies which way it's moving, and then he drives directly into it. Why? It's my personal quest to figure out why chasers are doing this and how we can stop accidents from happening. So one of my main takeaway lessons here is when you see something like this, stop. Okay, I correctly identify the structure. This is the bear's cage and where the tornado is going to be. Find a fixed point of reference, like a telephone pole, and then see which way is this thing moving. Okay, is it moving right to left? Is it moving left to right? Is it not moving at all? If it's not moving at all, it's coming right at me, and I need to take my escape route immediately. You can see very clearly this mass is moving to the left. It's going to cross to Mike Bettis' left, to his south. That's the direction he decides he needs to escape, is directly into the path. So my advice to chasers is to stop and just take a deep breath, don't panic, look and see which way this thing is moving, and then do not take an escape route across the path here. Because this is what's killing chasers. This is why I do this, right? I don't want to see any more friends out there get killed. I'm not trying to pick on people. I'm not trying to say, hey, you really screwed up here, you shouldn't have done that. Because these guys are gone and we can't get them back. I don't want to see other friends make the exact same mistakes and now they're gone too. That's my main motivation for doing this. So is to help going forward, correcting chasers, not fall into these same traps. And so my main fear with this latest event is we have people saying that this is the mesocyclone, this is a wall cloud, Paul's favorite thing to point out and identify on storms. But it's a mistake. This is an inflow band, and this is the main danger area of the storm. So I'm hoping that the people who are out there representing this community, who are in a position to educate chasers, a role model who people are looking up to, they are correctly identifying this and educating chasers, because I think people are mistaking this structure for a mesocyclone. They're saying, hey, this is just a rainy downdraft to the south. This is the main danger area here. I think that's really, really wrong, and we need to correct it, or else there's going to be more injuries and deaths out there. Instead, this is what we need to be identifying in this situation. We've got an inflow band and the bear's cage region here. Again, this is not a totally safe part of the storm. Tornadoes form here. There's severe weather here. But my main takeaway lesson is this is a secondary area of danger. This is your primary area of danger. That bear's cage area should be avoided, or else you're risking injury or death. And it's imperative that we identify this region here. So I love John Davies. He's a role model of mine. I've talked a lot about him at the Dupage seminars in the past. He went way out of his way to critique my last presentation, which was pretty awesome. But unfortunately, I think he's got it wrong here. And as much as it pains me to speak out against the people that I admire the most, I'm just terrified that if we don't correct this misinformation, that other chasers are going to get hurt and killed out there. This video in particular is talking about a previous close call that Silver Lining Tours had with the Joplin EF5 back in 2011. go and check out this video on YouTube. It's this really dramatic, gripping footage. And to me, what this highlights is that there is this pattern of behavior where storm chasers have just this gut urge to head south across the path of this tornado here. And I'm seeing this over and over and over again, is there is this pattern of behavior where when chasers need to flee, they're cutting south across the path. So I'm seeing the exact same thing here with the Joplin storm that this Silver Lining Groups tour has done again here. They're starting north of the path after the tornado has already been on the ground for a long time. It's been in progress for many minutes. Again, another giant HP supercell, and they're going to cut right across the path of it here. So I'm just trying to point out that mistakes and behaviors that chasers are making because they keep doing it. And if they keep doing it, people are going to get hurt and killed out there. So, and again, this is the Joplin storm, visually identifiable structure, inflow band, tornado to your south. Inside the inflow notch, north of the tornado, you do not want to be taking a southbound escape route across the path of this thing. So that's my main takeaway lesson for these types of events, is don't flee south across the path of this thing. Use those visual bearings. And if you don't have any visual bearings, you shouldn't be there in the first place, okay? Because you don't have situational awareness. So yeah, why is this important? I actually get some flack for this. He's saying hindsight is 2020 and you're Monday morning quarterbacking here. I think people are trying to dismiss the safety message here. What we're doing is not critiquing chasers and their past behavior. What I'm trying to do is develop generalized safety advice going forward that chasers can use to not make the same mistakes. Because what we're seeing the same patterns again and again in supercells, chasers making the same errors. So that's the goal of what we need to correct here. And these are not once-in-a-lifetime incidents. It seems like every other year there is a giant HP and there are close calls. Just in the past 10 years, here's a partial list of storms where there have been storm chaser accidents with damage to vehicles, injuries, and even involving tour groups. So the most infamous event, of course, was El Reno. There were actually tour groups that had some extremely close calls on that event, and that's where we saw the injuries and the deaths. But since then, there have been other close calls with tour groups, injuries, and so, yeah, this is happening a lot more than people think. And storm chasing has a level of danger that I don't think people are realizing. And so, yeah, the other big thing is, why are chasers doing this? Why are they cutting south across the bear's cage? Why are they driving into tornadoes? I don't know. There's got to be a mix of reasons. This is the best I could come up with. Some of them simply don't know any better. They need to be educated. Some of them are panicking and they have this knee-jerk reflex that they have to get out of there. And then I'm hoping that most of them are this. It's just I made a wrong turn. I lost my bearings. I wound up in a bad part of the storm that I shouldn't have been. Because when chasers are doing this more often, that's a correctable thing that's happening less frequently. Usually chasers are focused on getting out of that situation. These are the extremely dangerous ones that I worry about the most. It's where people are cutting across the bear's cage, they're core punching that rear flank downdraft because they don't want to lose their positioning on the storm. If I don't go south now and get back to clear air, the chase is over. That's it, we're done chasing. Or they just don't see the danger in the situation. We've done this 100 times. We haven't been hit yet. It's fine, we can keep doing it. This is what I hear this tour group saying, and it's extremely dangerous. It's like playing Russian roulette to me. You can spin that wheel so many times, but if that number comes up, man, it's game over. So I really want to point this out. And then this is one of my last slides here, just to kind of tie this together here in terms of storm chaser safety. Trying to figure out who's most at risk here and maybe how we can correct some of this. But I tried to plot as best as I could chasers who are in danger relative to their experience level, how much they're putting themselves out there in the paths of these tornadoes and into the bear's cage region, and how aggressively they're changing or chasing. And what we see here is those who are most at risk are in the most danger of becoming a storm chasing casualty. It's the people who chase the most and are chasing the most aggressively. So And this is what we saw on El Reno. It's the people who are deploying probes into the paths of the tornadoes, the Twistex team. And then on the other end of the scale is the opportunistic locals, people who don't know what they're doing. They don't know storm structure. They're waiting till a high-end event comes very close to them, and they're going to jump in their car and try to see it. So these are the people most at risk of getting hit and killed by a tornado, I think. And so this is kind of counterintuitive. Normally, I think you'd think that your risk goes down as you gain experience. But what's happening here is that the more you chase, I find that the more aggressive you get. I have to get that shot. It's the last day of the trip. My clients haven't seen a tornado. We have to get in there and find a tornado for them. Or I need to get my shot on the news. I need to get the money shot. So it's the pros who are putting themselves in harm's way more often. I think they're actually putting themselves more at risk. And I want to say, hey, you don't have to do that. You don't have to cut across the bear's cage. There's no good reason to do that for a crappy shot of an HP tornado that people are going to forget 5 minutes later. So my hope is that we can help people who are putting themselves more at risk, saying, hey, why don't you dial it back a notch? Why don't you take a look at the mistakes you're making, not fleeing south across the bear's cage? And also on the other side of the spectrum, helping the beginners and the newbies get to these more intermediate level areas where they're not putting themselves at risk because they've learned the ropes. There's always some inherent danger in storm chasing, but my hope is that by identifying these mistakes and educating new chasers on storm structure, that we can get chasers more towards this sweet spot at the bottom here, where their risk is minimized, because there's a whole lot of unnecessary risk-taking out there, and that can be totally avoided. So that's my safety message spiel, and thanks for having me, guys.
Thank you, Skip. I'd like to take a few minutes for questions. Rick, you've got something?
Outstanding. It was really excellent. Actually two quick questions, but I'll make this first one real short. The Kansas City radar was probably 60% further away from the Lone Star Lake, Kansas tornado, whereas the Topeka one was probably 40% closer. Did you notice that maybe the direction of the beam from the Topeka radar may have been kind of blunted out from picking up the smaller tornado vortex signature?
I looked at both Topeka and Kansas City, just seeing which site had a better fix on the couplet of the impacting tornado. And Topeka, by far, had the best fix on that tornado. I was getting much more. Kansas City was farther away. Kansas City was closer to the last half of that EF4 that hit Linwood. But further west, where the storm chaser accident occurred, I was actually getting much better resolution off of Topeka. So
real quickly, then the next one, you talked about these horizontal streamer vorticity. What was the last part of that?
Yeah, the streamwise vorticity current that Dr. Lee has identified is that.
Although that area is pretty flat, some of your videos showed some mountains in the background, and there is a slight upslope about 400 feet from that part of northern Kansas into maybe the parent cell. Do you think that may have had some slight increase in the ability for that streamer to get up into the storm?
Terrain absolutely plays a big role in tornado genesis, even on a small level, absolutely. And when I'm fascinated by Dr. Lee's talks. It's like rounding error in the math he's doing has a huge impact on what storm comes out of his models. So I know that in real life, it's little things like terrain differences, which are acting like that noise on that kind of level, that are definitely playing a role in what the storm eventually does with the tornadoes. So yes, it is, but what and how and why, I have no idea. So, yeah.
Hey, Skip.
Hi.
Okay. I can't hear it from here. I'm perfectly positioned in the dead spot. When NWS did their investigation, were they able to procure GPS tracks from the various parties involved?
I don't know how much the Weather Service actually looked into the actual accidents. I think they just noted the damage that had occurred at the time and the locations and the severity of it. I don't think they did an accident investigation. So I think that's, I didn't put this in the talk, but I think that's why it's important to do this, because if amateurs like me don't do it, then nobody does. We don't know what happened on these events. We don't know what went wrong. So yeah, don't know if they got any GPS data or not. So
This is not my area of specialty. I'm a microbiologist, but if a tornado and you were driving and a tornado were going in the same direction,
yeah.
can you generally outdrive a tornado or not?
Yeah. So there's a very famous video. I think it was 91, right? Andover. And so in the video, there's kind of this moment where they're like, we can't outrun it. We can't do it. And to be honest, I think they could have outrun it. They're on the interstate. You can go pretty fast. It's very, very rare for a tornado to go as fast as you can go down the interstate. The exception to that is if there's traffic. So if the traffic starts backing up and there's a tornado behind you, then you've got a problem. But generally, yeah, you can drive faster than a tornado if you're out in the open. The main thing, though, is if you're in a residential area, an urban area, or if there's traffic, then you've got a big problem. So to me, the main thing is clearing the path, especially if you're a spotter, chaser, get out of the path of that, and just avoid being in that situation in the first place. That's paramount.
Or a gravel road, maybe?
Yeah, you shouldn't, if you're in this position where there's a tornado behind you, and you've got no other options and you're running into traffic, you've already, to me, made several mistakes. And I want to help people identify, hey, you shouldn't be driving into that storm. There's a watch, there's a warning that you overlooked, and now we're literally a last-ditch effort here, considering leaving the car for the ditch or trying to outrun this thing. So to me, it's all about avoiding that situation.
Let me just make a final comment here, because it's kind of interesting, Skip, is not only do I have a problem with chasers relying on the accuracy and the precision of radar, because that is a dangerous thing. There's offset based on the elevation angle. There's interpretations that are wrong. I've seen plenty of times where the storms have this bent back, occluded front that goes back, and a new tornado forms further to the west, which is what this reminds me of. So relying on radar with a limited temporal and spatial resolution is a dangerous preposition. I also think that a lot of chasers now rely on it so much that they put themselves in places where they don't think about what the visual would be. One of my most common things when I'm out chasing is people go, well, what's that? I don't know. I'm not sure. And I see a lot of chasers who think they know everything of what's going on in the storm. And somebody who's done it for 30 years, there's times I'm like, I don't know. Just watch it for a little bit. I'm not sure. It could be this, and it might not be that. And it could be the wall cloud over there, or it could be tucked back in there, or there could be a secondary circulation. And it's amazing how many things are different in reality than what I would have conceived them in my head.
Yeah.
And I think that's a dangerous thing. That's why, we try to get people to chase with others more experienced for a while.
Yeah, absolutely.
Just keep in mind, I'd like to have, again, if you're interested in chasing, this would be a great trip to go on. This trip, number one, our assistant is going to be Dave Carlson, who's one of the lead forecasters from the Prairie Storm Prediction Center, which is the Canadian equivalent to our SPC. It's a great chance to learn a lot of this stuff. We run into Pecos Hank and Skip out in the field quite a bit. So talk to us. Skip, that was a great thing. One more thing I do want to say about Skip, and it kind of reminds me of being young, is that sometimes it takes courage to be outspoken and to take an opinion. And I admire that, because you're doing it not to attack. You're doing it to talk to people about lowering their confidence and going into a little bit more precaution. I think what you've done and the way you say things is really fantastic. So thank you for that.
Thanks, Paul.